No ar.
Good afternoon, everyone, and welcome back to the cycle of seminars of the Astronomy Department here at IAG. And today, the speaker of this week is Professor Martín Makler. And thank you, Martín, for accepting our invitation. And Martín got his PhD at CBPF, Centro Brasileiro de Pesquisas Físicas in Rio de Janeiro. And as of now, he's a researcher both at CBPF itself, as well as the International Center for Advanced Studies in Universidad Nacional de San Martín. And today, Martín is going to present the seminar Constraints on Modified Gravity Using Einstein Rings, Prospects for the LSST Era. And questions will be, as always, asked after the presentation. If you're following the seminar via our YouTube channel, you can write down your questions on the chat. And if you're following the presentation via Google Meet, you also have the opportunity to ask your questions after the presentation. And before the seminar begins, I would like to ask everyone on Google Meet to turn off your microphones and cameras. And Martín, you can start whenever you want.
Okay, so thank you very much for the invitation. I wish I could be at IAG-USP, but it's a bit far. I'm currently in Buenos Aires. So thanks to the organizers for the invitation. This is work of several people. I'll just mention some of them here, which have plots that are shown, but this is even a more extended list. So this is a collective work. So I'll start by introducing a little bit what strong lensing is, how is the modified gravity setting in strong lensing. Now, I'll discuss a little bit what will happen with SST, and then how as I would argue, we will need machine learning for LSST, and I'll discuss very briefly how to find, model, and extract the systems we want using machine learning. And then I'll discuss recent work we've been doing, like preparing for LSST with recent data and getting more data with SOAR. So questions are very welcome. So the motivation of this specific work, I'll be discussing a little bit of modified gravity. So there are several reasons for us to seek modifications of general relativity, despite it being a very successful theory of gravity. One of them is dark matter and dark energy, which we don't know what it is. So some modifications of gravity have been proposed to account for dark matter or to dark energy or both, but usually they are not successful. I would say that nowadays, most of the modifications of general relativity are targeting more dark energy than dark matter. Dark energy, it has, okay, I think people got, there were many intents to, many trials to explain the accelerated expansion of the universe with dark energy. And I think people got a bit tired of that and then tried to modify gravity. The point is that nowadays there are sets of theories of modification of general relativity. They are compatible in smaller scales with general relativity, let's say in the scales of galaxies, and which produce in larger scales the accelerated expansion of the universe. And these theories, they have a transition, which is very interesting from general relativity to a modification of gravity. And the scale where this modification occurs has to be larger than galaxy or maybe even cluster scales. And there is a possibility, though not a necessity, that something interesting could be, or measurable and interesting could be happening at the outskirts, let's say, of galaxies. So this interesting behavior of some models of modified gravity are some of the motivations to seek to measure these modifications of general relativity in the scales that we will discuss today. But in any case, we always want to test our theories in all time and mass and energy scales. So you may think of as a test of general relativity, regardless if you like or not modified gravity to explain the accelerated expansion of the universe. The point is that we are able to design a test of general relativity or a test of an aspect of general relativity, which holds in the scales of galaxies in several kiloparsec scales, and that will be the topic of the discussion today. So our object of study will be galaxy lensing systems, which are also known as Einstein rings, even if it just are multiple images or arcs. We're going to call them Einstein rings. The typical situation is where the galaxy, the front galaxy and the galaxy in the back are aligned, and you are able to form a complete ring. But this nomenclature will apply to strong lensing by galaxy. So just to have an idea of what's going on, I will skip all the math in general, and if there are questions, we can work them out at the end. But just to have an idea of what's going on, how we can use strong lensing to test gravity. This is the metric, so it's a way to express the gravitational field in general relativity. And so this is a time, this is space. We are working in a curved space-time in large scales, which will be represented by a Friedman-Lemaitre-Robertson-Walker metric. So the usual metric of that we describe a homogeneous and isotropic universe. And this is coded here. So this is a space in this context, in the cosmological constant. This is time. And light propagates in null geodesics. So ds square is 0. So you may think of a space divided by time, like a velocity. If I make this equal to 0, then I can make quote unquote light speed. Of course, light speed is always c, but we can think of this as a effective light speed propagating in a curved space-time, where you have a mass with a potential phi there. And in the weak field limit, so for phi over c squared much smaller than 1, we have this expression. So we can compute a diffraction index, c over c prime, and this diffraction index is greater than 1. So the light propagating in a gravitational field behaves exactly like the light propagating in some medium with a varying refraction index. And indeed, we can make real concrete simulations of the effect of gravitational lensing using pieces of glasses and so on. I will not go into this today, but we can discuss some examples. But the fact is that in the standard general relativity, we have the gravitational potential appearing in two pieces of the metric, and it's the same potential in the usual situations. And the effective refraction index is given by this potential here, right? So a light feels the combination of these two phis, which is the same here, but as we will see in modified gravity, is a bit different. So okay, this deflection angle, if we work a point mass, is given by this. So we think we are here observing. We have a nearby galaxy. We have a distant source of light, which is a galaxy too, and the light will propagate, will be deflected, and this is the deflection angle. And this is the expression of the deflection angle, which was, by the way, the first time was measured during an eclipse in 1919 in the Sobral city in Ceará and also in Prince Island. So this deflection is computed using this metric. It's twice the Newtonian computation. And this distortion of the light will produce the gravitational lensing effect. So here is a more, let's say, detailed idea of lensing. Here's the distant galaxy. So we call this source. Here's a nearby galaxy or galaxy clusters. This is the lens. And light propagates through bending. So light bundles, they propagate through this bending of space-time. If the mass of the lens is massive enough, and if the lens source and the observer are aligned precise enough, we'll have these strong lensing features like arcs or multiple images or rings. If you go a little bit further, arclets, and even further, a very weak signal that can be measured, but will not be the topic of discussion today. And the point is that lensing is like a mapping between two planes. So one is the plane where the objects are, like, let's say, in truth, what we would see if there was no lens, and we call this beta. And what we see, the angles that we see after the bending of light, we call them theta. So we call this source plane, and this the lens plane. This is what we see, and this is what we would have without lensing. So the mapping between these two planes is exactly how we will see the images distorted. And the mapping is given by this equation. So you have the gradient of a potential, and this is weighted by these distances from object to source, object to lens, lens to source. So these are cosmological distances. And this potential here is given by the integral along the line of sight from the source to the observer of this potential, which is like the Newtonian potential. So it's clear that the lensing has, let's say, a cosmological dependence because of the cosmological distances. And of course, it's depending on all the astrophysics of the lens. Okay, so today we will assume the distances are known by many other observations in cosmology, and we'll focus more on what happens here close to the lens. Okay, so we'll study the potential, the effect of the potential of the lens. Okay, so what is strong lensing? As we mentioned, it's a propagation of light through new geodesics, and when the effect of this distortion is strong, we have the formation of multiple images or very strong distortions, large magnifications, because the surface brightness of the source is conserved through gravitational lensing. If we see an image which is larger, we will also be getting more photons. So it's really magnified. And also because of the achromaticity of this effect, it doesn't depend on the wavelength, then the lenses can act as gravitational telescopes. We don't distort the spectrum of distant galaxies. So the actual spectrum of the image we will see is the actual spectrum of the source. And of course, they are a probe of the mass distribution in the lens because we are measuring this potential phi, besides being a probe of cosmology because of these distances, but this is not something that we will explore today. And traditionally, we see these images of strong lensing, which are very sharp, thin features. These are images like from the Hubble Space Telescope. But from the ground, what we see are more like this. Arcs are, in general, low surface brightness features that are also easily erased by the effect of the PSF. So finding them in actual images is not trivial. And I'll mention this in a little bit. So once we have a strong lensing object like the one shown here, where we have here multiple images of the same source, this is a gravitational arc, but it's made by the merger of multiple images. We can infer properties of the mass distribution, and just a pictorial idea is given by this example here, but I'll mention a more sophisticated modeling, and we can discuss this in the questions. But the idea is that we have 3 images of the same source. So we will have a model for the mass distribution. We have some position of the source that we don't know. And the model of the mass distribution will depend on the ellipticity, the orientation angle, the mass of the lens, so parameters of the lens. The idea is that I'm observing here 6 quantities, so the coordinates x1 and x2 of these 3 images, and I want a single position of the lens to be mapped by the lens equation to the 3 positions of the 3 images, okay? So we can make a chi-square and find the parameters of the lens and the position of the source by this method. So that's the idea, okay? I want to project the 3 images in the same source, and by doing so, I'm able to extract properties of the lens. We are able to do a much more sophisticated procedure and also reconstruct the light distribution of the source. But this will be discussed in the questions, if there are any. But the idea is that the more multiple images, the more constraints, the more sophisticated I can consider the lens of the model of the lens. And so if I have a lot of a surface brightness variation in the images, I can use them. So the more information I have from the images, the more constraints I can make the distribution, the mass distribution of the lens. Now, everything I said up to now, well, some of the things I said are regardless of the theory of gravity, but when we discussed the deflection of light, I considered a metric which had the two potentials here, which are shown in this metric, they were the same, right? So if we go further and we consider modifications of gravity, one of the possible effects of considering a more general theory of gravity is that there are 2 potentials in the metric, so 2 scalar potentials. There are other components of the metric that we can discuss, which is their role, but for what matters here, there are 2 scalar potentials in a more general metric theory of gravity. The rest is the same as I discussed before, but the point is that in general relativity, for the usual metric content that we consider, the 2 potentials are the same. So we define a quantity named sleep parameter, which is the ratio of these 2 potentials. So if we are in GR, in general, this gamma will be equal 1, okay? And in modified gravity theories, gamma can be different from 1, can be 2 or a half or many things, can be space-time dependent. So the point is, if I find gamma equal 1, it's compatible with general relativity, it doesn't rule out all theories of modified gravity. However, if I measure gamma clearly different from 1, basically this rules out general relativity. So what we will aim here is a way to measure gamma, okay, in the scales of strong lensing. Okay, so I go again to the argument to find the deflection angle and the effect of the bending of light in general. But now we have the same metric, but we have two potentials, right? And if we make the same argument that the light propagates in no geodesics, and I compute some sort of effective light velocity, doing the same procedure as we did before, then what we will find is that this is effective light velocity will be given by this. So in the weak field limit, again, we have this factor here. So the difference, considering modified gravity or general relativity, is that now I have the sum of the two potentials and not twice the same potential. So if I use that gamma that I defined before, which is the ratio of the two potentials, right, I can rewrite this as 1 plus gamma over 2 times 2 phi over c squared. So I can define sort of an effective field, an effective potential, which is just 1 plus gamma over 2 times the standard one, okay? So what we aim is to measure this. So the point is that if I look at the propagation of light, I get this sensitivity to the two potentials. However, if I look at massive particles, let's say stars that are in a virial equilibrium in a galaxy, or anything that's massive enough that's not relativistic, then the dynamics of this object will be given only by the G00 component, only by the time component. So basically, the motion of matter is given by this potential. Also, this potential is directly connected to the density. Okay, so if I use a combination of the lensing with dynamics, like motion of the stars, then I would be able to differentiate phi from psi. I would be able to measure a gamma that's different from 1. So that's the whole idea. So the motion of massive particles, non-relativistic particles, is given just by the potential phi. Sorry, here I switched the nomenclature. And photons are sensitive to the sum of the potentials. That's the idea behind, right? And how can I recover this potential here from the motion of stars? That's the Jeans equation. And how I can recover the sum of the potentials? By the lensing. So that's the idea. Through the kinematics of the galaxy, for example, we are able to recover phi, and through the lensing, we're able to recover the sum of the potentials. Okay, I'll give an example which is super simplified, but I think it's useful pedagogically. It will show us how things work. So I will consider now a very simple model of lens, which is a singular isothermal sphere. So this model is not what we use in practice. We use a more general model, but it's good enough. I mean, it does fit more or less well the density of galaxies. So it's not just a pure toy model. It has some usefulness in nature. Okay, so this is a singular isothermal sphere, and in this case, this sigma v here is a velocity dispersion. And so if I look, for example, at the dynamics of galaxies, I look at the broadening of some emission line of the galaxy, for example, due to the motion of the stars in the galaxy. So I measure velocity dispersion. I'm measuring the velocity dispersion from the dynamics. So I'm probing this field phi. If I, in turn, use lensing to measure the potentials, I will measure again the same density profile, like here, because this density profile will yield these potentials, but it will have a difference of 1 plus gamma over 2, right? So what I measure from the broadening of the lines, from the velocity dispersion in a spectrum, for example, will be connected by the velocity dispersion that I infer from the shape of the dark matter density and the potential. They will be matched by this 1 plus gamma over 2. So in principle, if I have a list of systems where I measure the velocity dispersion and I measure from the dynamics and I measure the velocity dispersion as a parameter in the density profile that produces the deflection of light, I am able to measure gamma. That's the whole idea. Although in practice, as I said, many things are different when we make a more serious modeling. Okay. So in the real world, it's not isothermal, it's not spherical. It's not a single isothermal sphere. It doesn't have a single velocity dispersion. It may have an anisotropic velocity dispersion, a radial and a tangential velocity dispersion. Of course, there's a lot of observation effects. What we measure is not the central velocity dispersion. We measure like an average of velocity dispersion within a fiber or a slit. Anyway, so there are lots of factors of realism, both in terms of the modeling of the lens, but also in accounting for all observational issues, right? But this is taken into account. We can discuss this in the questions. And basically, there are two ways of exploring this. One way is to make a very detailed modeling of the system, if you have a HST image, or using interferometers like in ALMA, and you have a very detailed information on the image. Also, you have an integral field unit spectroscopy of the lens. So you can make really a detailed mapping of the dynamics and of the lensing. And with a single system, you're able to measure gamma. So an example is this paper, as the only example I know, by the way, is this example in using one system where gamma is 1 ± 10%. So it's a 10% measurement of gamma compatible with general relativity. By the way, Cristina Furlaneto and Carlos Melo, her student in the URGS in Rio Grande do Sul, are doing some very detailed analysis of another system. So we may have a second like this one. But what I'm discussing today is the opposite kind of measurement, where you have a very broad, a single measurement of the velocity dispersion. You have also a broad, not such high quality image in terms of strong lensing, but you have a lot of systems. So you can make a statistical measurement of gamma, okay? So in this case, we have to deal, as I mentioned, with these observational effects that we measure some average velocity dispersion. We have to assume some shape of the density profile, for example, a power law. We have to assume a shape from the light distribution, and also a function, which is this anisotropy of the velocity dispersion. But all this can be accounted for, as I mentioned. And a result, more or less recent, is that we have also gamma compatible with 1 with a 4% statistical error. However, when we look into the details of all the systematics that can go into this kind of modeling, the systematic error may be up to 25%. So what we want to address as a motivation for the work I'm going to discuss today is, on the one hand, to improve these statistics, so having more systems. Here is about 100 systems, quite a heterogeneous collection of systems. And we aim, on one hand, in the future to have more systems, but also understanding much more the systematics by doing more careful, more detailed, more homogeneous analysis, okay? So just to start, let's say, warming up, we implemented this machinery to account for all these models that I mentioned before. And instead of looking at this same data set that's mentioned here, and that was used in several analyses of modified gravity, we just go blindly to a large collection of systems, of strong lensing systems, and we blindly select those systems, and we have a new sample with some selection criteria that I'm putting here, and we just run this machinery. So again, we assume a constant anisotropy velocity dispersion. We assume density profile, which is a power law. We impose global priors on these quantities. We just reproduce what's done in the literature. So we use the same priors. It's different data set, but the same priors. So we are using a global priors on these quantities, right? Not a galaxy by galaxy, for example. And these are quite strong priors. And what we obtain is what's shown here. So basically, the sleep parameter is consistent to 1 with a 2% error. So that's quite surprising. Or maybe not surprising, but the point is that we are able to, again, put a limit on gamma, which is nice because this is like a blind analysis, but also, I mean, that shows the power, but also the danger of running this machinery with the same assumptions and so on. Aren't we just getting the same result because we are imposing the same, let's say, exactly the same kind of assumptions? So is this like a confirmation bias, right? You set some parameters, and you obtain what you want to obtain, what you think, maybe it's general relativity, and then you're happy. So we want really to revisit all the steps of this modeling, loosening these constraints, looking at brand new data, and so on and so forth. And that's part of a program, systematic program, that we started undertaking now, okay? And one of the points is increasing the sample size. And this will take us to new data, to new surveys. Right? So let's see what's the landscape of gravitational lensing systems. Since the discovery 5 years ago, so in 30 years, about hundreds of systems were discovered. Some of these surveys, not the larger ones, but some of the surveys were carried out by our group, including Eduardo Cipriano in IAG-USP and several people in Brazil, like Sogras and CS82. But okay, there were several of these systems, and they accounted for these hundreds. Then in the last 5 years, with the wide field imaging surveys that have a good imaging quality, like let's say like about seeing about 1 arcsecond, so better than SDSS. So this new generation of deeper, wide field, good resolution surveys, like the kilodegree survey, like the dark energy survey, hypersuprime chem, and several others. Also a combination with some spectroscopic, massive spectroscopic data, they led to the discovery of thousands of systems. So we have an order of magnitude increase in the systems, and also because of the large number of galaxies to be inspected to find gravitational arcs or the wide fields to be searched for, we started needing automated arc finding, and this is something I will mention in a few minutes. Okay, so one example is the dark energy survey, but all of these current surveys, they use some kind of machine learning way of finding these systems. And in a few years from now, with the new generation wide field surveys like LSST, Rubin, Euclides, Roman, WFIRST, and also with the spectroscopic surveys, we expect 1 or even 2 orders of magnitude increase in the number of systems. So for example, Rubin will see half of the visible sky per night. It will identify about 10 to the 10 galaxies. Okay, this is only like on the co-eds of all images, but there is a lot of information in the time domain too, besides some very deep fields that will be observed. So as I said, the number of systems will increase by 10 or by 100. And we absolutely need codes, automated finding of these systems, right? But not only that. Until now, we were using, let's say, machine learning to find the systems, but then we carried out some visual inspection, and then the modeling, then recovering the mass distribution of the lens, recovering the shape of the source. And so the analysis of the system was done in a manual way, system by system. Some student or some researcher was doing a system by system analysis. This would not be possible with the large number of systems that we would discover. So also we start needing to carry out automated analysis. In the last few years, there were several papers along this line. I'll discuss just a little bit of this. Okay, so the first thing now is we should be able to find the systems in an automated way, and we should be able to model them. To address the first thing, a simulation was carried out as a challenge, so a competition, international competition, to try to identify gravitational lensing. Then a second one was carried out, not only to find the systems, but now to model. So classification, as we use in the machine learning jargon, classification and regression, classifying things as lenses and non-lenses, and measuring things out of the systems, like measuring the Einstein ring, for example. We participated in this first competition and also in the second one. So I'll discuss just the result of the second one. It carried out Euclid-like simulations, so simulations in the infrared and in one visible band. So the group at CBPF, which was led by Clécio Debon, entered this competition. And there were 2 key aspects of the work of the group. One is that there was a lot of person power involved. And the second one, there was a lot of GPU access involved. And these 2 things were key. So what the team did was a lot of work, right? Testing many architectures, testing many pre-processing, testing different combinations of data sets. And at the end, we had what we thought was our best result. So we submitted 4 different classifiers to this challenge. And we also submitted 2 regression entries, okay, 2 attempts to measure the Einstein radius. And as I said, there was a lot of person and a lot of hardware effort. And part of this hardware effort is because we have a project involving Petrobras, so the Brazilian oil company, state-owned oil company that invests in research. And CBPF has a project with them, and we could use GPUs that were within the context of this project. So I said there was a lot of teamwork, was in our summer vacations and over Christmas, and they were working a lot. And all this effort paid, was worth, because we won this challenge. So the best score on finding the systems was obtained by this CAST. Efficient net is the kind of convolution neural network that was used, and CAST is the CBPF ARC search team. Okay, so of the 4 entries that submitted, many other groups participated, and our 4 entries were out of the best ones, and we had good regression results, but I don't think there was like a winner. They focus more on the classification results. But this is the team. So this is CASLEO. This is Patrick Schubert, which I would like to to pay honor to him. He deceased very tragically. Okay, so anyway, so this is the team at CBPF that was involved. So in the paper, we acknowledge Patrick Schubert's work. So this was our finding. Now let's look a little bit more in the regression part. So more recently, there was a paper on Nature that was proposing to use also neural network, not only to find, but now to model the systems. So the neural network was trained in simulations, and then it was applied to real data. So these are the big dots here. And the point is that the neural network was able to recover the Einstein ring to a very good precision. So here's another example by a student of the group, by João França, which also used simulations, but both to train and also to validate the prediction of the Einstein ring. And so this is the architecture. This is the simulations they use. But the bottom line is that you are able to recover pretty good the properties of the lens. And here they show that the neural network can do as good as a manual modeling. Okay, so this is a result also by CASLEO that uses a simulation that simulates the dark energy survey conditions. So it's a very simple mass model. It's a single isothermal ellipsoid. Then it simulates all these systems with DES quality data. But the point here is to use information on several bands. So they work with 3 bands, okay, only 3 bands. And the question was, okay, can we recover the Einstein ring? Can we recover some information on the redshift of the lens? Can we recover some information on the redshift of the source? And these are the results. Okay, this is the Einstein ring, the Einstein radius, which is recovered with a 10% uncertainty and 20% outliers. This is the redshift of the source, which is very poorly constrained with a lot of outliers, which is expected. Very weak distant galaxies. It's very hard to have a photometric redshift of the sources. This is the photometric redshift of the lens, which also has about 10% uncertainty, about 20% outliers. And this is when we try to recover the velocity dispersion of the lens. So these results for me was very impressive. It's not fully clear to me why this is so. I mean, why is the neural network measuring so well the velocity dispersion? My understanding is that this is the geometric factor of lensing and not any measurement of the velocity dispersion, since we don't have any spectrum. So this is akin to the velocity dispersion parameter that we measure from the lensing, right? Which is a combination of the Einstein ring and the cosmological distances. But the combination of these 3 quantities, the 2 cosmological distances and the Einstein ring, to yield the velocity dispersion is such that the velocity dispersion is very well measured, with a much lower outlier and with a higher precision. So this is specifically interesting if we know that the sensitivity to testing gravity is to the velocity dispersion, right? So what we wanted to check here is, okay, is this useful for testing gravity? Okay, so since we have this apparently ability to measure so well the quantity to which modifying gravity is sensitive, so we carried out a very simple simulation where we simulate a fictitious velocity dispersion. the idea is that I'll be having spectroscopy of these systems. I will measure the velocity dispersion of the lens, okay? And now I'm just using the standard errors on the velocity dispersion to generate a mock sample of velocity dispersions. So now I have, let's say, in a column, the velocity dispersions recovered by lensing, and in another column, the velocity dispersion with the scatter and so on, measured by spectroscopy, a mock. Okay, but these two tables is like what I showed in the very beginning. By comparing the two, in principle, we should be able to measure gamma. So that's what we did. We asked if we can recover gamma in this way. Of course, it's a simulation. So in the simulation, we chose gamma equal to 1. And we made a selection based on the previous plot of a good range of Einstein rings. And what we get as a result is that we are able to recover gamma to within 2%. Again, this is purely simulations, okay? But what we are using here is an image simulation, which was trained an image simulation which was used to train a neural network to measure the Einstein ring. So what we are using here is the lensing information recovered by this automated machine learning method. And on the other hand, we are using a simulated velocity dispersion with error bar and so on. And when we use this, we are able to recover gamma with a low uncertainty. So that only tells us that within the simulations, of course, but the fact that we are recovering the lens parameters using machine learning is not biasing the measurement of gamma, right? And this is what is important now. Just would like to ask a question because the internet is sometimes not very good. Are you hear me well?
We can hear you perfectly, Martin.
Okay, great, thank you. So we can continue. All right, so that's a pretty, well, for me, it's a motivation. So let's see, we would like to test this in the real world. So the bottom line is, in LSST, where we will have a much larger sample, but if we can carry out what we've been discussing, so finding and modeling the systems, and provided that we target a selected sample of systems with spectroscopy, then we will be able to measure the velocity dispersions, the modified gravity parameter from LSST data, right? The question is, are the simulations good enough to ask this question? That we'll be able to measure gamma, yes or no? We know that the simulations do not account for many degrees of realism. For example, from the challenge 1 to the challenge 2, on the classification, the systems perform very differently. So these two simulations are very different. And usually, as we are dealing with convolutional neural networks, so deep neural networks, we usually need a lot of systems for the training, let's say 100,000 systems. So if I want to train in real data with such a large number of systems, then why I need to apply this to LSST? I mean, this is the number of systems we expect to find at the end, right? How can I use them to train? I have thousands of systems today. So we asked the question, what is the smallest size of the sample that we can have to have reliable or meaningful measurement of let's say, of finding the arcs? What's the minimum size of the sample I need to train with real data? Okay. Oops, sorry. So that's the question we asked using the simulations. But what we did is we have, let's say, in this example, 14,000 simulated systems. Okay, and we want to train and test. In this example, are two machine learning methods, two convolutional neural networks, to recover the systems, to find, to classify. And this is a measurement of how good this is using the area under the rock curve. And what we see is, yeah, okay, when that sample is very large, we have a very good ALK, a very good area under the curve, a very good behavior of this finder. And as we go down the number of samples for training, we, of course, decrease the quality. But it's quite amazing that we still have 0.9 when you have about a few hundreds of systems. Let's say with 500 systems, we are still able to get a significant area under the curve, which is 0.9. So this is also very motivating. You say, look, with hundreds of systems, I may be able to train this neural network. I don't need to use the simulations. On the gravitational lens finding challenge 2, the situation is a bit less good. So we need about 1,000 to reach 0.8, but it's still meaningful. So, I mean, the idea is that if I have few thousands of systems, I should be able to train these classifiers, these arc finders, using real data. So our aim now is to collect this real data, okay? So the simulations, are they good enough? We don't think so. They're useful to learn many things, but they don't account for many degrees of realism. So we went ahead, and the idea is, let's build the largest compilation we can find of these systems so that we can use them for training, on one hand for classification, but also for regression, okay? Our aim specifically is to use the systems to test modified gravity, but as I mentioned, they have many other applications. Some are just measuring cosmology, but also modeling the lens, or even studying the sources. So this, of course, is a sample that has several applications. We also want to use this large sample to select interesting systems that we're going to follow up, that we're going to get better data, for example, velocity dispersions through spectrum, okay? And we want to tag this large set, classifying the systems in Einstein rings, arcs, multiple images, quads of QSOs, if they are in clusters, if they are in early type galaxies. We want to tag these systems and maybe use this to train many machine learning classifiers, like in ImageNet, but focusing on strong lensing. So to compile this large sample, we look at many catalogs of strong lensing, identified in many different ways. We combine this information in a single catalog, and that's a bit painful, remove duplicates and many other things. And once we have this large consolidated collection of strong lens systems or candidates, we go to the wide field surveys that are available today, like the Legcy Survey, DES, in the future we include Delve, and so on. Also surveys we were involved in, like Blink, CS82, etc. And then we make cutouts of all these systems. So we have cutouts of these systems under different situations, under different surveys, that we can also use to compare the effect of the scene, the depth, and so on and so forth. This data set, the cutouts on one hand and the catalog on the other hand, the catalog was cross-matched with photometric catalogs and with spectroscopic catalogs. So we have about 70 papers that went into this collection. We have about 30,000 of unique objects, so unique candidates of strong lensing. We had about 15,000 images cutouts in the wide field surveys. About 12,000 of these systems, they have photometry, and about 5,000 of them have spectra. And all this is the work of Renan Alves, who is a PhD student that is about to complete his PhD. So if you're looking for someone, hire him. So these dots show the distribution of the system candidates in the celestial sphere. These are the contour regions are some of the wide field surveys that went into this collection of postage stamps, right? So this is about 380 single images that can be combined. I mean, some objects have many bands and appear in many surveys. This is just a collection of some systems, they look really nice. So as I said, one application is to tag these and to use to test machine learning. We didn't do that yet. Another application was to use this selection to target new data. So the idea is that we will improve the number of systems that are used to constrain gravity and also to address the systematics. So we found a lot of these systems, which we wanted to make a selection of known redshift of the lens and known redshift of the source. So systems that we knew we can model them, and we targeted them to have a better measurement of, or a first measurement of the velocity dispersion. So we carried out a SOAR program this year on semester A and semester B. It was just completed a few weeks ago, and we observed 23 systems seeking to measure the velocity dispersion to use it directly in the measurement of modified gravity. So this is a sample of 20 of these systems. The first 10 were observed in the first semester. and the data of them is already reduced and available. This is a work by Ingrid Bellotto from IAG-USP and Eduardo Cipriano. These are 10 of the systems that were observed this semester. Some were also observed or had prior data. For example, we observed this system with Gemini too, so we'll be able to compare the SOAR and the Gemini results. This system, we learned, it's been observed by James Webb Space Telescope. So some are measurements for the first time, some are available in the literature. That's an example of a reduced spectrum. So the black line is the spectrum, the red is a model used in the FIT. These are the residuals. And the point is that from the 13 systems that we observed, 10 of them could be used to measure the redshift, the velocity dispersion. Actually, some of these systems, just because of weather conditions and so on, we could not reach the full integration time we wanted. So really, it's 10 systems that are usable in this sample of the first semester. 9 of them have signal to noise above 10. 3 of them has signal to noise above 20. We wanted to reach high signal to noise because the uncertainty of the velocity dispersion correlates very well with the signal to noise. So, for example, of the systems, 7 have an uncertainty on the velocity dispersion that's less than 10%, and about these 3, I think they have a velocity dispersion less than 5%. So that's what we want. So the spectra was modeled using this penalized pixel fitting routine method. And we revised a little bit our strategy. So the point is that we reached basically the signal to noise we wanted for the brightest systems, not the dimmest one. And we revised a little bit our strategy for the data of 2020B. So we devoted more integration time to the dimmer systems. So we hope that we have even better results for the second semester. But the point is we have a new sample where we can carry out the computation of the sleep parameter of modified gravity. Now we need to model also this at strong lensing, and we have a pretty detailed way of carrying out this modeling. So we take very careful care of the light distribution of the lens, of the light distribution of the images, of course. Okay, I will not go into the details, but this is a several-step procedure in the modeling that provide us the parameters of the lens, okay? So this modeling is done for all the systems, also for the first semester. And we derived the gamma ppn for 3 of these systems, which were the 3 that were available a few weeks ago with both the strong lensing modeling and the spectroscopy. So for only 3 systems in our sample, again, we were able to derive this gamma ppn equal 1 plus minus 20, so about a 20% measurement of gamma. This is very surprising and motivated with only 3 systems. But this is, again, using the standard modeling. What we want to do now is really exploit this sample that we have. So for now, we have new and independent, and in general, higher signal-to-noise measure of sigma v. So we have really a new sample, totally independent, that we can perform the measurements of the sleep parameter. But also we can carry out a consistent modeling of the strong lensing with the modeling of modified gravity. In the previous examples, the lens is modeled from HST or from the ground with a single isomer sphere, but then it's used power law. It's a bit, let's say, messy. We want to use self-consistently everything that we measure on the data. We want to measure. Another difference, we are only using images from the ground. That's what we'll have for LSST, not any modeling from space as in the previous sample. So it's more homogeneous as from the ground. We are measuring the slope of the light distribution, and we want to use this for every single lens and not like a global prior. Again, we are fitting this power law, and that's what we will use, not a global prior. So both the light distribution and the lens model, they will be used self-consistently in the analysis. I did not mention here, but we are also testing different models of anisotropy. We can discuss that later. So we can really carry out more self-consistently modeling on a system-by-system basis with this kind of data. And in the near future, we want to move on from using single-slit spectroscopy, which was what we used in this study, and now exploits all the information on the images that cover a wider field using the integral field spectroscopy. So we have already applied for integral field spectroscopy in SOAR. We had applied for Gemini. So the idea is now to use and exploit the spatial information, not only in the images, but also in the spectroscopy that has a lot of advantages that I won't have time to discuss. And in the future, and this is also thinking of using completely new imaging data from Delft survey, which is a new survey that compiles all DCAM imaging. And they have a lot of new systems that were not discovered before. And in the future, we want to test this with a new type of detector in the spectroscopy, which are skipper CCDs that we can discuss also in the question session. So just a summary of what we've been discussing. The galaxy strong lensing plus kinematics, stellar kinematics in the galaxies, they can enable us to test gravity at scales of 10 kiloparsecs. If we use archival data, we agree with the previous estimates. We have been using new data, like getting velocity dispersion of new systems. We also confirmed some of systems that didn't have a spectroscopic redshift of the source. The idea is to get spatially resolved information and use this in the modeling. And we also want to revisit all the procedure that has been used to model these systems, like using no global priors, getting the information from the data, the seeing from the data, spectroscopic data. That's very important because the seeing is what spreads up, makes like an average velocity dispersion. We want to account for this in an accurate way. We are also testing, everything is with a constant velocity dispersion. We are now testing models of the velocity, the anisotropy of the velocity dispersion. And we want to continue making tests on simulations of what we will be able to do to recover with Rubin, Roman, or Euclid. Regarding specifically the compilation that we did, which is our focus was to use this for measuring modified gravity, but as I mentioned, has a lot of possible applications. So we made a compilation from a large set of catalogs with images from all the main wide field imaging surveys. This is to increase the sample of systems for this kind of science, but also to enable us to make follow-ups of interesting systems. And we start to see very nice results from our campaign with SOAR. But we also want to use this to train many types of application of machine learning for classifying, for regression, also for segmentation and more. Now we are carrying out a detailed modeling of the systems that are in the sample, as I mentioned, the work of João França. And the idea is then to use this modeling to test the regression. At the end, wide field surveys like Rubin, LSST, will revolutionize many aspects of strong lensing. I discussed just one of them. And of course, we need to be ready to use this data. And essentially, that means using reliably machine learning. But there are many other applications. For example, we will be able to find multiply image type 1a supernovae. And that is like golden lenses with many, many interesting applications. And this will be enabled by the time domain information of Rubin. And that's all. Thank you.
Thank you, Martín. That was actually awesome. And it was pretty clear. And I know nothing about gravitational lensing, so this says a lot, I guess. If anyone has any questions on Google Meet, you can raise your hands. So, Professor Laet, go ahead.
Hi, Martín. Congratulations for the very interesting talk to you and all the team. Huh?
Thank you.
Because I understand that this is a large collaboration.
Yes.
You need, say, percentile, a few percent accuracy in gamma in order to be able to test for modified gravity. I wonder if some unknowns like substructure in the source, things like that, can't affect with an amount even larger than this thing that you are expecting. Huh?
Yes.
So there are many, I can imagine, many different sources of many difficulties that may increase the error in a way that is not clearly controllable. Could you comment?
Yes, that's a very good point. There are many potential sources of systematic uncertainties. I mentioned some of them, not all of them, and we are addressing some of them. So that shows us that we have a significant large team, but not large enough to be addressing all these questions. So I mentioned some systematics. You mentioned other ones which are possibly relevant, like the substructure in the lens or the substructure in the source, right? On the source side, we are addressing this because we are recovering the lens properties using a parameterized source, like a SIR6 profile, where you have few parameters, or a complete pixelated modeling of the source. And what we see, and maybe I have some plots. Let me see. Yeah, if you allow me, I can look to the backup slides. I have some example, but the bottom line is that when we carry out these two types of modeling, which are quite different in terms of the modeling of the source, the results are the results for the lens parameters. They are very much in agreement. So it seems that the recovering of the global lens properties, like the Einstein ring, is not. I'm not sure I have the. Okay. Yes, that's an example. No, that's not the example I meant. No, this is a comparison of two codes. Okay, sorry, I don't have the slide I wanted to show you, but I can say just in saying that perhaps I have an example of just how we model. Okay, this is an example with a parametric source. So this is the data, this is the image plane that we recover, and this is when we use a pixel-based reconstruction. What I don't have here is the comparison between the parameters. But the bottom line, at least in a few systems that we've been working, and this is João, as I mentioned, the parameters of the lens are very much in agreement with the two methodologies. So I don't think the source will be a big source of systematic, the way we model the source, for this kind of science. But yeah, we have to test different models from the lens, substructure in the lens. There is a large path to be sure that we control the systematic. So we are, yeah.
Just a suggestion that came out in my mind. You can use simulations, PNG simulations, things like that, because they, although the resolution might not be quite good, but you can use this sort of simulations to see whether what would be the effects of the lens substructures or other parameters of the central region of the galaxy in the gamma.
Yeah, that's a good suggestion. Actually, I mean, we could use TNG for sure. Still, we are in small scales, but also several years ago, maybe 10 years ago, with a student, Gabriel Caminha, we just simulated substructure. We just had a single lens, and we just thrown substructure as a fraction of the mass, so totally by hand. But we could test the impact of the recovery of, let's say, the Einstein ring in this kind of simulation. That was a old style simulation using Lens 2, which is another software. But the bottom line, and we can look at his PhD thesis, the bottom line is that for global parameters like the Einstein ring, it doesn't seem to be like a key thing. So by hand-waving argument, it doesn't seem to be biasing the theta Einstein results. But what we could do very simply is to make a simulation by which we just vary the theta Einstein by, let's say, 10% systematically or just randomly, and see what the effect is on gamma. We didn't do that. That's something that should be feasible. So that's a good.
Mm-hmm. Thank you, Martín.
Yeah, thanks for the question.
Okay, so Professor Reinaldo has a question. Actually, Maria Vitória.
Okay, thank you. Thank you very much for this very clear talk. Me, as Guilherme, cosmology is not really my subject, but I would like to ask you about the sleep parameter you mentioned that if you get of the order of the unity value, you would have GR, right? How far from unity are the, let's say, most favorite theories of modified gravity? Would you expect a very different value from one?
So that's a very good point, because you could be saying, well, okay, what's the expected deviation what's the deviation you expect from, let's say, modified theories of gravity, right? And that's part of let's say the problem that in many theories of modified gravity, in most theories of modified gravity, you need a screening mechanism so that gravity behaves like GR in some small scales. What the problem is that in many models, this transition happens at larger scales than those that we are probing with galaxies. So it's perfectly fine to have a gamma that's equal to 1 where we are measuring, and it has larger deviation as large scales. Okay, so there is not like an expected value of gamma different from 1 for the most favored modified gravity theories. So we are not like ruling out a large swath of theories by saying that gamma is equal 1 plus minus 1%, let's say. So so I think this is the bottom line. I mean, we are looking at predictions of gamma from different theories. I can have examples like using Rondeski theory, and I can tell you, well, if you give me the parameters of Rondeski theory, I tell you what gamma is, right? So we can do that. But there is not a preferred value of gamma that we are ruling out with these constraints. So as I said at the beginning, there is like a motivation to look for these deviations because there are lots of proposals to modify gravity. Some of them could have gamma very different from 1 in the scales we are looking for. So these were not ruled out previously. We are ruling them out, but does not rule out large categories of systems, of theories, okay? Many theories do have gamma equal 1 in the scales that we are. So it's really like we are not ruling out theories, but we are just constraining the set of theories that they have to satisfy our constraints. Also, a second point is that the extent to which we can set constraints on gamma depends a lot on the distances. So like in solar system distance, we are able to measure gamma, I don't know, 1 to 1 part in 10 to the 5, perhaps. I don't have the numbers on the top of my head. But the constraints on gamma, they vary a lot in the different scales. In the scales of galaxies, what we have by this kind of study is as good as we can have by other methods for now. So that's one of the best methods to constrain gamma in that scales, although this does not rule out a large category of modified gravity.
Okay, thank you very much. That was a really clear answer. Thank you.
So just a further comment on that you may say, well, GR is good. So why are you doing all this job, right? Because why ruling out modified gravity? I say, well, it's perfectly fine. You can do other things with this sample, but almost all the treatment I mentioned here is the same. For example, if I want to constrain the density profiles of lenses using this set of data, the modeling would be very similar. If I want to constrain the cosmological distances, the modeling is very similar. If I want to constrain the curvature of the universe that you can measure also with this data, there is an interesting paper on Nature on that, is also the same modeling. So the kind of modeling we are doing and the kind of studying the systematics, my personal interest is in gamma because that's the quantity that's like almost the only way to measure using this data. But other scientific focus, they will benefit from the same studies of systematics that we are carrying out here.
Hi, Martin. Another question. Thank you for the talk. I misunderstood when you were describing the results from the machine learning techniques. I understood that the machine learning outperforms all the other conventional techniques for recognizing the arcs, right? Yes. And I remember you mentioned that machine learning was also being to be applied to analyze the data. Is it so?
Yes.
Did it outperform conventional methods?
It was, well, okay. So
Because my doubt is that I understand that machine learning is exceptional for recognizing patterns, but for analysis, I'm very curious to see how much machine learning can do.
Right. So, so regarding the classification, yes, it outperforms, and even it outperforms human eye, which was quite astonishing. So in the first challenge, one person entered the competition just by looking at the images, and he lost. So yes, it's better in classification. So now in regression, that the first paper I mentioned as a Nature paper, the test that was really carried out was on data. So there's not like a true value. So the result is compatible with the modeling using the physics, but you cannot say which one is better. In those systems here, the few squares are the real data. So the only thing they say, well, the results from the detailed modeling are compatible with the machine learning. We cannot say if they outperform. And in the other example I have shown, we are only comparing the machine learning with the true. So I haven't seen a comparison in simulations where you can control everything of the recovery manually using this lens inversion codes and the machine learning. So that's a good question that you're asking. This is something we wanted to do because now there is like a pipeline where you can use the manual modeling, but in a pipeline. There is a paper by Thomas Collett, No Lens Left Behind, where they do this. So that's totally feasible. We wanted to look at that. Just run on the simulation, the recovery using more traditional inversion methods and the machine learning. But we don't have this question yet. So that's a very good question. And I hope we can tell you the answer at some point soon. Yeah.
Thank you. Any of the new technology, I really don't know how it's done for microlensing in the galaxy. Some of the technology that are being developed in software can be applied to microlensing.
That's a very good question. Actually, we are working on that on the microlensing side too. The physics is very different because we have these light curves, right? And we have to identify the brightness variations, a function of time. But yeah, so there are two ways of doing that with machine learning. One, it's called MicroLEA. It's a software that's available on the web, MicroLEA. And the MicroLEA uses the more conventional machine learning, like extreme gradient boosts, like neural networks. I think uses some kind of boosted decision trees. Anyway, it has like some more conventional methods that are based on features of the light curve. So you provide lots of light curves, we measure some features of these light curves and train. And so we are testing these on simulations that are done for the LSST. On the other hand, again, the group by CASLEO is also looking at these light curves in the same challenge of LSST, but with a deep learning method, with a long short-term memory method, LSTM. So this LSTM is performing very well on the simulation data. So this data, just to recap, is a simulation of light curves. You have light curves from supernova, from, eclipsing binaries, tidal disruption effects, microlensing. So 14 categories of time-varying astrophysical objects. And you train them, the simulation of all these light curves, we are able to recover. So apparently, yes, machine learning is also proving good to recover the microlensing systems within this soup of transients. I don't know if this answers your question.
Yes, thank you, Martin.
So, okay, let's thank Martin once again. And thank you, Martin, for accepting our invitation and for your talk. And I guess we see each other next week.
Thank you so much for the invitation, for the audience, and for the questions. See you next time.
Thank you, Martin. And for all of those you here at IAG, even if you are following via Google Meet, we have coffee break. So come down here.
Bye-bye.
Ciao, Martin.